So we're going to leave the world of EIGRP behind us, and at this point we're now going to move into another interior gateway routing protocol, which is Open Shortest Path First, otherwise known as OSPF. So let's just do a quick introduction to OSPF. First thing is that OSPF is and always has been an open standard. There actually is an RFC for it if you want to Google the RFC for OSPF. But it's not owned by any company, it's not proprietary. It's always been an open standard. It's actually very, very old as well. It's been around for several decades at this point. So OSPF uses something called the shortest path first algorithm. What does that mean? Well, unlike EIGRP, which is what we classify as an advanced distance vector protocol, OSPF falls into a different category called a link state routing protocol. One of the big differences between the two of them is that a distance vector or advanced distance vector protocol, all it knows about as far as the topology is concerned is itself and its directly connected neighbors, and that's it. So if you and I are running a distance vector routing protocol, I will tell you about all the routes I know about, so you know that to get to those routes, you go through me. So you know those routes live back here somewhere, but you don't know what the topology looks like back here. You have no idea what is connected to what the links look like, no idea. Whereas in a link state routing protocol, you actually know the entire topology, not just you and your directly connected neighbors, but everything. You can form like a map in your own mind as to where all the routers are, where the subnets sit on each one of those routers, and you can piece it together. So the shortest path first algorithm takes place after you've built that map in your mind. It's sort of like spanning tree, where you're like the root of the tree and everything branches out from you. In the shortest path first algorithm, you build this tree and then you figure out from your perspective as you at the center of the universe what the shortest path is to any given destination. That's the SPF algorithm. Like EIGRP, OSPF utilizes hello packets to dynamically discover and build OSPF neighbor relationships. In the case of OSPF, we actually call them adjacencies, OSPF adjacencies. So I'll use those terms interchangeably. Neighborship, adjacency, meaning basically the same thing. Like EIGRP, where the vast majority of EIGRP packets went to a multicast address, most OSPF packets also go to multicast address. As a matter of fact, OSPF has two addresses that are reserved just for itself, 224.0.0.5 and 224.0.0.6. OSPF hello packets always go to 224.0.0.5. The other packets that we're going to talk about with OSPF may go to .5 or they may go to .6. When we get a little bit further into this and I talk about this concept of something called designated routers and backup designated routers, the idea between these two different addresses will make a little bit more sense. OSPF also works based on an area hierarchy, minimizing LSA flooding. What does that talk about? Because we haven't talked about areas or LSAs yet. Let's hold off on that bullet for just a minute. The very next slide is going to go into a little bit more detail of what that acronym LSA means. And once I talk about LSAs, then I'll be able to give you a better understanding of what an OSPF area is and why you might want more than one area. And like pretty much all the routing protocols that utilize neighbors, OSPF has the optional capability of supporting authentication, both clear text and MD5 authentication. Okay, so the real heart and soul of OSPF are these things called link state advertisements. What is that? Okay, first of all, remember that in OSPF we call this a link state routing protocol. In other words, if I'm a router and this is what I would normally call an interface, like interface fast Ethernet 00 or interface serial 00, OSPF calls that a link, not an interface, a link. Technically speaking, everything that has a subnet would be considered a link. So if I have a subinterface, that's a link. If I have a physical interface that has 2 or 3 subnets on it, that would be categorized as 2 or 3 separate links, even though it's on one physical interface. So it's a link we're talking about. The next thing is, as an OSPF router, if I'm directly connected to this interface right here, let's say it's Fast Ethernet 1, then it's my responsibility to create a special type of a packet called a link state update packet, an LSU. I'll go ahead and write that on here. LSU, which stands for link state update. And within that link state update packet, I will pack in there one or more link state advertisements. So an LSU packet, think of that as being like in EIGRP terminology, an EIGRP update. An EIGRP update contains one or more networks inside of it, one or more prefixes that update is carrying. Similarly, an OSPF link state update contains one or more LSAs inside of it. Now, what exactly is an LSA? Okay, so let's say I need to advertise information about this link to all the other OSPF routers. Well, I'm going to create inside my LSU, I'm going to create a data structure called a link state advertisement. And that link state advertisement is going to give you everything you need to know about this link. Now, before I go into the details of that, here's the main thing I want you to think about. Number one, the overall goal or objective of OSPF is to build this topology map in its mind. It wants to build this tree of what the entire topology looks like, who's connected to who they're connected to. That's its overall objective. So imagine, just close your eyes for a second, imagine a whole bunch of circles and you're starting to draw lines between those circles and you're building a tree-like structure interconnecting these circles, and the circles are representing routers and the lines are representing links connecting them. So you're building that. And then as you build that, imagine you start sort of writing in the various subnets where they live on top of the links. That's sort of your secondary objective, is to figure out where the subnets are. But your primary objective is to build this tree, build this SPF tree. Okay, so the link state advertisement, that's its main job, is to help you figure out this topology. So as such, when I create this link state advertisement describing Fast Ethernet 1, I'm going to tell you a whole lot more than just what subnet lives here. You see, if I was a distance vector routing protocol, that's all you'd care about, is what subnets I'm connected to. You could care less about anything else. In a link state advertisement, I'm going to say, this is a broadcast link. This link has a certain bandwidth. Let me tell you about all the neighbors I'm connected to on this link. Oh, let me also tell you about the subnet on this link as well. I'll actually tell you all sorts of descriptive information about this link in my LSA. And now, here's another big difference. In the world of EIGRP, let's do some contrasting here. Let's say that you and I are two routers connected via EIGRP, and behind you, you have another EIGRP neighbor relationship with someone behind you. So I send you an EIGRP update. In my EIGRP update, I say, hey, my name is Router Keith, that's my router ID, and here's a bunch of networks you can get through me to reach. Okay, now what do? When you turn around and send an EIGRP update to your neighbor, do you tell your neighbor about me, about my router ID, and that these networks you learned from me? No, you don't. Let's say your name is Sally. Well, when you turn around and you send an EIGRP update to your neighbor, all you say is you copy those networks I gave you and you say, hey, my name's Sally, neighbor, and I'm Sally and here's the networks I know about. So your neighbor knows about the networks are reachable through you, but your neighbor has no idea that I'm the one who actually told you about those networks. And similarly, you have no idea about who told me about those networks. Well, in OSPF, it's just the opposite. If I create a link state advertisement and I package one or more of those inside a LSU, a link state update packet, and I multicast it to you, you take that link state advertisement and stick it in a database, you store it, and then you keep right on flooding it. You don't change anything about it. So even if there's 9 or 10 routers behind you, they will all know about me. They will know about my name. They will know that I'm the one that created this LSA, that I'm the one who owns this link. So they will be able to, in their mind, as they're putting their jigsaw puzzle together, they will know that I exist and where I sit. And they'll know that I'm connected to you and that you and I are neighbors, and I'm neighbors with some other people here. So the LSA gets flooded to all these other routers, And that's how they build this topology diagram. So an LSA is carried within a link state update packet, and different types of LSAs carry different data. So this is another important ingredient. So at the CCNA level, they don't really expect you to know the details of what exactly an LSA is, and that there's different kinds, and what the names of those different kinds are, and what different purposes they serve. But you sort of get the idea here that there are different kinds of LSAs, and they do different things depending on where a router sits in the topology. And LSAs age out after 1 hour and are refreshed every 30 minutes. So what that means is that this LSA I created describing this link, when I flooded it to you, and then it got flooded to all the other people out there, well, you and I are exchanging hello packets, just like an EIGRP. You and I are exchanging hello packets, and that's how you know I still exist, that I'm still a valid neighbor, because every few seconds you're getting a hello packet from me. Now, if we were doing EIGRP, once I sent you an EIGRP update with some networks in it, you might never see an update from me ever again. I might never tell you about those networks for an hour, a week, 6 months. Hey, as long as you and I are still exchanging hello packets, you say, hey, Keith still exists. So that routing update that Keith sent me about the 7575 network 3 months ago must still be there because he hasn't told me it's not there. OSPF takes a different approach, because remember, that LSA that I flooded to you also was flooded to all the people behind you. So yeah, it might be well and good for you and I to exchange hellos and you know that I'm here, but how do they know I'm here? I'm not sending hello packets to the people behind you. I don't have a neighbor relationship with them. I have it with you. So at some point in time, the people behind you might be saying, it's been a while since we got some LSA from some guy out there named Keith. Is he still alive? Is he actually still reachable? So in OSPF, we say, well, when an LSA goes out, there's a timer associated with it. If you don't get that LSA refreshed 1 hour later, it purges from your database. You delete it. You say, okay, it's been an hour, haven't heard from that guy, he must be gone. I'll delete the LSA. So as the owner of the LSA, as the person who actually created it, it's my responsibility every 30 minutes to refresh that LSA. So I will reflood it every 30 minutes. Okay, so let's go back to what we were just talking about, this slide right here. And I want to pay some special attention to works on an area hierarchy to minimize LSA flooding. And this will hopefully make a little bit more sense now. So let's look at this topology diagram right here. So there's a lot of rules that go along with OSPF, and this is why some people don't like OSPF, because there's a lot of rules to remember about what it can do and what it can't do, and what one router's job is versus what another router's job is. So I'm going to give you one of the rules right now. So one of the rules states that if you ever receive an LSA describing that something in the tree has changed. All right, so imagine for a moment, you're an OSPF router. You've had some neighbor relationships going now for several hours or several days. Everything's been nice and steady. You're exchanging hello packets every few seconds. And you've built this nice tree. You know where everybody is, where everybody's sitting, and you got this nice tree in your mind. Now all of a sudden, boop, here comes in an LSA from some other router out there who says, there's a new link in the tree. Or who says, an existing link has changed, it's gone down. The rule of OSPF states that when that happens, you have to take that nice tree and rip it apart. It's like taking your jigsaw puzzle and ripping it apart and then build it all back together again, accounting for that new LSA. Now, that's an important point. Here's why. This process of building a tree is very CPU intensive. It takes the brain of the router a lot of power to put all these LSAs together, to see who connects with who, and to eventually build this map of the topology in its mind. So every time an LSA comes in and says, oh man, I got to rip apart my tree and now rebuild it with this one new jigsaw puzzle. Or if an LSA comes in and says, this branch is gone, this link is gone, oh, I got to rip apart my tree and now rebuild it and exclude that branch. That takes a lot of processing power for the router to do that. So imagine for a moment that we're looking at this topology right here. And let's say that there's some link in this topology that is not very stable. Maybe it's this link right here. Okay? So that link is flapping. For whatever reason, it's going down, and it's coming up. Going down, coming up. Well, every time that happens, these two routers here, router 4 and switch 3, are creating new LSAs about a link down condition or a new link coming up condition, which means those LSAs are being flooded all over the place. And so every time that happens, all these devices are having to tear down their tree, rebuild it. Tear down their tree, rebuild it. So in OSPF, when you configure OSPF, you're going to start by doing router OSPF, and then you're going to give it some process ID. And I'll talk more about the process ID coming up in another video. And then, like EIGRP, you're going to have some sort of network command. And let's just take switch 3 as an example. I'll have a network command to cover this network, and this network. But unlike EIGRP, every link in OSPF is considered to be part of an area. Let's start real quickly and just say that, well, we're going to have all these links in this entire topology be in one giant area. Now, an area, like an autonomous system number, has a value. If I'm having my entire topology in just one area, that area can be whatever I want. Well, maybe we'll say area 8. So in switch 3 here, I'd have network 232 in area 8, network 333 in area 8, network 343 in area 8. And that would be enabling OSPF on these links so we could start speaking about it. So you could do that. You could have every link in your entire topology in one giant area. Now Cisco recommends, there's actually a design recommendation that says you should have no more than about 40 or 50 routers total in any one given area. So right now this is easy, right? Because I've got 1, 2, 3, 4, 5, 6, 7. I've got about 7 devices. No problem. Here's the problem though, or the potential problem. Within an area, everybody has to know the entire topology of that area. And everybody's database that's storing the link state advertisements has to be the same. And this is another rule of OSPF. If you and I are OSPF neighbors, and we are what's called fully adjacent, what that means is that all the LSAs I have in my database, you have to have them. And whatever you have in your database, I have to have them. Our databases have to be synchronized. They have to look identical. So in this particular topology here, all 7 of these devices would have their own LSAs that they created, as well as the LSAs of all the other devices in here. So even in this small topology as we see here, that'd be a fair amount of LSAs. We've got 1, 2, 3, 4, 5, 6, 7. We've got about 8 links. So we'd have several LSAs. So all 7 of these devices, if you looked in any one of them, their link state database would be identical. They'd all have exactly the same LSAs. And this is the reason why if a new LSA comes in, everybody's got to add it to their database because they're synchronized, and they have to tear apart their tree and rebuild it. And then if another LSA comes in, synchronize it to their database, tear apart their tree, rebuild it. Well, if my topology is fairly stable, I don't really have to worry about that. It's that environment I talked about earlier where I says, hey, a link's flapping, and now it's causing the CPUs of my routers to get pretty high because they have to keep having to tear apart their topology and rebuild it over and over again. So OSPF, the designer said, we're going to give you a way to avoid unnecessary CPU computations in that type of topology. Here's what we're going to do. What you can do is you can take your topology, and instead of putting all of it in one area, you can divide up into multiple areas. So for example, I could say that all of these links here are in area 8, and all of these links are in another area. Now the rule of OSPF, here's another rule, third rule. The rule of OSPF says if you have 2 or more areas, one of them has to be the backbone area. The backbone area. And that has a special number reserved, area 0. Now I could have made the green area, area 0, and I could have made the red area, area 8. Doesn't really matter as long as one of these 2 areas was area 0. Okay? So now, why might I divide this up into 2 areas? Here's why. A router only has to know the full map of what the topology looks like of the areas that it is connected to. If there's other areas out there that this router is not connected to, he has no links in those other areas, he doesn't know what those areas look like. They're just like a cloud to him. He'll know what subnets live there, what networks are out there, but he won't know what that topology looks like. So for example, router 4 over here. Router 4 knows exactly what's inside this green area. He knows all of this. But as far as what's in this red area, just think of that as being like a cloud. Router 4 will know that the 222 network exists, that the 121 network exists, that the 111 network exists, and that they're all reachable via switch 2. But he won't have any idea what the topology looks like behind switch 2. That's sort of like a distance vector characteristic, actually. Now, switch 2, because he's connected to both areas, he's actually going to have 2 trees that he has to build. He has to build a Shor's path tree for area 8 and a Shor's path tree for area 0. And he's actually going to have 2 databases. One database for all the LSAs he's collected in area 8 and another database for all the LSAs he's collected in area 0. So he's going to have to work a little bit harder. As a matter of fact, when a router such as switch 2, I'm calling him switch 2, but we're just treating him as a router. When a router connects to area 0 and one other area, when he's sitting as a border between the backbone area and a non-backbone area, he actually goes by the name of an area border router, an ABR. So why is that important? Well, let's go back to this link right here. So when switch 3 came online and I activated OSPF on this link, he created an LSA that described that link. And that LSA got flooded to everybody. Now that LSA is, I'll just give you a preview of it. I said there's different kinds of LSAs. This LSA here in green that I'm describing is called a type 1 router LSA. The primary objective of a type 1 router LSA is to help construct this tree, help build this SPF tree. A type 1 router LSA will get flooded within an area, but it has to stop at the area border router. In other words, all these devices in here in the green area, area 8, they need to see each other's type 1 router LSAs. That's what helps them build this topology. But those type 1 router LSAs will stop at switch 2. They will not be allowed to go into the backbone area, into area 0. Similarly, there's going to be type 1 router LSAs that are generated here in area 0, so that all the devices in area 0 can know what their topology looks like, and they will stop at the area border router. Now you might be thinking, wait a second, if those type 1 router LSAs stop at the ABR and go no further, then how is area 0 ever going to learn about the routes over here in area 8? And how is area 8 ever going to learn about the routes over here in area 0? That's one of the special things the area border router does. He says, well, I'm not allowed to flood router LSAs from one area into another area. I can't do that. So, what should I do? Why don't I create a different kind of an LSA? An LSA whose purpose is not to create a tree, not to create any kind of topology information, an LSA whose sole purpose is just to describe networks, just describe what subnets live in various areas. And that's what the ABR will do. He will actually create a special type of an LSA, actually several of them that will go out this way. And these LSAs will say, hey, I'm your ABR, I'm switch 2, and you can use me to get to the 232 network. or the 323 or the 333 or the 343. You can get there through me. I'm not telling you what the topology looks like, but with this special kind of LSA, I'm just saying there's another area you guys don't know about in area 0, and you can reach those subnets through me. So that's why the ABR is very special. Once he realizes, oh, hey, I connect to the backbone area and one or more non-backbone areas, he says, okay, router LSAs stop with me, and I have to generate a different kind of an LSA so that these two areas can learn about the routes that live there. So that's why we say that OSPF works on an area hierarchy, So just to once again put that into perspective, if I have one area, that can be whatever I want. But if I have two or more areas, like this, and maybe like this, then the area in the middle is going to be my backbone area, which is area 0. The other areas can be whatever I want them to be. Maybe this is area 20, and maybe over here, this is area 77. But the main idea is that everything has to flow through the backbone. So even theoretically, let's say I had a router here who is like this. Say this is router X. Router X has a link in area 20, he has a link in area 77. Is he an ABR? No, he is not, because he is not connected to area 0. So as such, router X does know what the topology looks like in area 20 and what the topology looks like in area 77, but he is not allowed to send routes from area 77 into area 20 and vice versa. Anything he learns about in area 20, he is not allowed to send those routes into area 77 because he is not an ABR. So these other routers right here that are between the backbone area and the non-backbone areas, these are my ABRs. So routes will always be learned from the backbone and then into non-backbone areas. That's the way routes will be learned.